Hello, everybody. In this episode, I'll be speaking with Peter Hase. Peter is an AI researcher who just finished his PhD at UNC Chapel Hill, where he specialized in natural language processing and interpretability research, with a special interest in applications to AI safety. For links to what we're discussing, you can check the description of the episode, and a transcript is available at axrp.net. All right, Peter, welcome to AXARP.
Yeah, thanks so much, Daniel. I'm excited to be here.
Yeah, I'm excited to have you on. So, my understanding is that most of your work is in interpretability, roughly interpretability in language models. Is that fair to say?
Yeah, that's right. Yeah, I've been in an NLP lab for my PhD, so we work mostly with language models, but a lot of it in terms of like methods, evals has been focused on interpretability.
Actually, maybe one thing I want to ask is, I have the impression that you were into language models like even before they were cool, doing NLP before it was cool, right? So I just today I like looked at your Google Scholar and like scrolled down to see the oldest paper you were a co-author on, and it's like this 2018 paper on algorithmic sonnet generation. So yeah, 2018, like before the rest of us had caught up. Like, what got you interested in NLP?
Yeah, well, I remember the project you were talking about. That was when I was an undergrad. I feel so lucky to have had the opportunity to do a little like special projects class actually with Cynthia Rudin at Duke in my undergrad. And gosh, I mean, I was interested in language. I was interested in psychology and linguistics in my undergrad, and very interested in language, and increasingly interested in machine learning and statistics. And so it was just a great intersection of the topics and learning about language models, and which at the time were really LSTMs. And getting an opportunity to apply those to a fun task. I'm not. I would even then. Of course I admitted it wasn't necessarily that consequential poetry generation, but it was certainly a great opportunity to get to work with language models a bit.
Yeah, I guess like you mentioned, the bulk of your work has been in interpretability. What got you interested in that aspect?
Yeah, that was also an interest that developed in undergrad. So I think a long time ago, there are many different arguments put forth for like why interpretability was like a good thing to study. Um, at the time, there was definitely a very intuitive draw, and there still is an intuitive draw that it's just good to know how these things work. It's just good to know how AI systems work, how language models work. They're doing increasingly interesting things. I mean, at the time, there's so much progress in vision, and this was 2018, so there'd been a lot of progress in RL, language models. I think by 2018, GPT 1 was out, and I think GPT 2
Hmm.
was coming out like spring 2018 or 19. Um, and it was just very clear that these systems were making a lot of progress and doing just fundamentally interesting things. And yeah, from a safety perspective, it's like, gosh, we should know how they work. We should be able to explain their decision making process.
This is kind of a broad question, but how would you say interpretability is doing as a subfield?
Well, this is a great question. Yeah, I tend to be, I think, optimistic when talking with people from other subfields or who are working on, capabilities research or other research areas. And I probably come off as a little bit pessimistic when I'm talking with my colleagues
Hmm.
about this. Yeah, let me be clear. There's definitely a lot of progress being made, where we have better evals, we have a better understanding of like, okay, when do we have a ground truth? When are we kind of like speculating about the reasoning process? What would it mean for an interpretation or an explainability method to be useful, and what could it be useful for downstream? This picture has just become a lot clearer in the past 5 to 6 years. I'll say that, yeah, one of the reasons I'm pessimistic, at least when it comes to colleagues, is like we just end up talking about all the false positives and false starts, and like, oh, the reason this result didn't hold up was because of this, or the reason this result didn't hold up was because of this.
Right.
So and I think some of this is like decently high profile. Like people might know about things like feature attribution or saliency maps. So this was a popular and one of the first kind of major methods for trying to get a sense of what neural networks were doing, and you could think of this as being like a 2015 to 2016
Hmm.
method, which was to say, okay, like what if you have a vision model, what's it looking at? Is it looking at, the dog in the image? Is it looking at the background? Is it looking at a human in the image? And people were really excited because this was one of the first ways to generate. I mean, the images just looked good. The visualizations looked good, and you could say, "Wow, it really seems like the neural network thinks this is a husky because it's looking at the snow in the background, and not
Mm,
because it's looking at the dog per se." Yeah.
right.
So people were really excited about these methods, and then if you've worked in the subfield for a while, you know how these methods have had a bit of a fall from grace, and they didn't turn out to be useful in human studies for the most part. There's been theoretical work showing that some of these popular feature attribution and saliency methods can do no better than random in certain settings.
Mm.
There have been a lot of hard learned lessons in the subfield, in terms of what to trust and what's promising to run with in the long term.
I'm wondering if you have like an agenda of just like questions you think that it's important for the interpretability field to answer, and if so, like what are they? Like where should we be looking? What should we be like aiming for here?
I think we're still in the stage of figuring out what methods are good and what evals tell us when we've created something useful. So it's I don't think we're yet at the stage where it's like we have the tools and we're mainly interested in detecting bad reasoning processes or detecting deception in language models. It's not yet at we're not yet at the stage where we're just trying to like catch safety failures. We're still at the stage where we're trying to build tools that would let us catch safety failures, and we're trying to build evaluations for the tools so we know which tools would work at that.
Yeah.
So it's still pretty upstream. Um, yeah. I'll stop there and actually ask you to like maybe elaborate on the question a bit, so I can keep going. Yeah.
Yeah, I guess so. I guess it seems like a view of sort of more basic science.
Mm,
Like we just like the reasons to do interpretability is we know that like something about understanding model behavior, understanding model internals, why things are happening, like that something around that is going to be useful. And like if we did some more basic science, we would just have a better sense of what the important questions to ask are. Is that roughly like a good glossary review, or am I missing something?
okay. Thanks. Yeah. Okay. Yeah. So the research stage we're at, I think, is still basic science. Let me give what I think. So I gave the kind of intuitive motivation before for interpretability, and why I think that's an exciting area. It's we want to know how these things work. They're so fascinating. They do such interesting things. We want to know how they work. This is the intuitive pitch. I think the strongest pitch that has emerged over time for interpretability research is that we need something that goes a little bit beyond testing. So all models get tested on all kinds of data sets, benchmarks, evals. We're looking for dangerous behaviors. We're looking for dangerous capabilities. We want to know what kinds of reasoning and knowledge that models possess. So really, I think the best pitch for interpretability is what can our tests not catch?
Hmm.
So one thing that our tests can't catch a lot of the time is the underlying reasoning process. So if we just have a huge multiple choice exam that is going to tell us if the models have dangerous bioweapons development capabilities, or the models have really strong theory of mind, such that they could like operate in a social setting and like either be cooperative or intentionally deceptive. If we just have like surface level, let's prompt the model and see what text it outputs kind of tests for that thing, we can't test every scenario. We can't exhaustively test every relevant scenario. There are settings where we'd be interested in deploying the model when it's interacting with people. It might be more or less knowledgeable or aware that it's interacting with people. And there's going to be settings where we can't actually test the thing we're interested in, or we can't exhaustively test the model. And that's especially the setting where we want to open up the hood and figure out what's going on inside and be able to say, okay, yes, it did this multiple choice problem correctly, and it had a really impressive, strong reasoning process for how it got there. And we're pretty sure it's actually going to generalize beyond just the things we're testing. Or we haven't deployed it in a setting where it is cooperating with people in the real world yet, but we've leveraged some interpretability method to say, yes, this model fully intends on cooperating with people. even if it knew that it could like slightly better optimize, one of its incentives at the expense of like harming a human. We know it wouldn't do that because we've been able to like truly inspect its reasoning process underneath.
So I've been doing this like interpretability work for a while, right? What what things do you think we've learned out of interpretability research?
Yeah, so I think one big thing we've learned is that um, we really want the methods to be useful for some downstream purpose. So
Hmm.
that means when we have an interpretability tool, like we're inspecting what features the model relies on, we want that to enable us to do some debugging. We want that to enable us to catch failures that we might not have been aware of before. We might want that to like make the decision making process more clear to an end user so they can decide if it was reasonable or not, and they might like that this comes up in for instance this problem called algorithmic recourse, where like a person is like being classified by a model and like they want to understand like why they got the decision they did.
Hmm.
So a lot of it's like increasingly gearing our evals towards these downstream use cases, so that we can make sure that we're actually getting like good signal on the methods we're developing. Yeah.
Hmm.
So that's one broad lesson I think, and I could say a little bit more about I think some of the more upstream evals that still seem valuable to me, but that's one lesson. So that's like figuring out methods that actually improve safety of models in some tangible way, basically, and going back to what I said before, especially in a way that's complementary to testing or complementary to other kinds of evals. Um, yeah, I think one of the other lessons is this will be more object level. Um, we're learning that language models can generate really plausible sounding textual explanations of their decision making that aren't actually how they're reasoning. So this
Right.
this is just an immediate object level lesson about how language models work. Uh, it's their ability to chat with people is really impressive. Their ability to offer like justifications for their answers is really impressive, and we're starting to catch them out in inconsistencies via some cleverly designed tests that show that what the model says is not really what it was thinking a lot of the time. Yeah, that's I think a very important insight in terms of like interacting with the models in text, and I'd say that's more of in the natural language explanations category in terms of like what research stream that is. And then
Sure.
there's this area of mechanistic interpretability and other kinds of probing research historically in NLP that is that I'd say is a setting where we're really gaining traction on figuring out how models represent things. So a lot of the work in 2015 and 2016 was focused on looking at the input and okay, what part of the input is this model looking at? And for vision models, you'd get heat maps that would like light up over a part of an image that the model might be looking at. In a
Right.
text setting, you'd get text highlights. So you'd say, oh, it's these words, and we're going to highlight them, and that shows you what the model's looking at. I think we're really starting to go deeper than that. We're really starting to be able to say, okay, here are the hidden activations in the model. And there's been one development I'll point out. It might have been that we used to say, okay, here are the neurons, and here are the neurons that represent this, or the neurons that represent that. There's been some really interesting mathematical progress, I think, on showing it's not just individual neurons, but it's particular combinations of neurons that might represent a certain feature. So you turn this cluster of neurons on, and that means like the model has definitely detected that like this text is discussing soccer as a sport, or
Right.
you have this other cluster of activations or neurons that have been turned on, and it's like, okay, now it's discussing soccer as like a political phenomenon or like governing bodies of soccer, and it's like different very abstract features of model inputs. We're starting to connect the dots between those abstract features and model internals and how the models are actually representing them inside, and then after that, how the models are using those representations. So we might know that, okay, the model has detected something, and now how is it going to influence the decision? And people are developing tools for saying, okay, yes, this feature has been detected, and it plays an important role in the model's answer.
So okay, your first 2 points of things we learned, like it's important to like it's important to get some sort of downstream benefit from your interpretability method, or peg it to does it actually help you do such and such task?
Mm.
And large language models are really good at faking explanations of how they're thinking. These seem these sound to me like kind of negative results, right?
Mm.
Like
Mm-hmm.
you might have thought this thing was true, but it's not true, right? You might have thought that just because you have a plausible story for why this like integrated gradient method like tells you something about the model, you're just wrong, and actually you should just test it against like does it actually help you do something? You might have thought that like if the thing can talk, it's gonna like say something reasonable. That's not true. Does that seem like a fair characterization to you?
Yeah, sorry, to be clear, those basically were negative results. I mean, we were
Yeah,
realizing
yeah.
that some of our evals weren't really demonstrating external usefulness or downstream usefulness, and the natural language stuff, um, yeah, it's just I think people were some people, I think, not in the explainability world, when they saw things like these like dialogue models get developed, or like chain of thought get developed, or like RLHF models get developed,
Hmm.
and they saw models explaining reasoning in words to people. I mean, I certainly saw public perception from NLP people, experts in the field,
Hmm.
basically say, "Wow, like we just almost solved explainability, right?" Like,
Right, right.
and it took some additional studies to say, okay, no, this is a result we've seen before. Like, we have a new explanation method, and it still doesn't quite tell us what's going on inside the model.
So if I'm trying to think about like kind of what we learned there, it seems like the underlying theme is you might think that neural networks are sort of neat and tidy, such that like there's like a place where a thing is happening, and you find the place and you understand the thing, um, and it's just not true. Like 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 somehow the story of interpretability is just like falsifying naive models of how neural networks work, and the way we falsify them is we get a thing that seems like it should work and it turns out to not be helpful. um and somehow the point of it is to just like help us realize how alien language models are.
Yeah, I think that's a good way to put it. And I think this is one reason um, people are starting to notice a need for more ground truth evals,
Hmm.
and being able to say, okay, here's what we know that the model's doing, because we specifically designed a neural network to reason in a certain way, or to like be vulnerable to certain adversarial examples, or to rely too strongly on a certain input. Or sometimes people do that with language models. Sometimes people do it with just very toy neural networks that like learn a specific function, and the goal is simply to figure out what that function is.
Hmm.
Yeah, so this is a setting where, yeah, we to avoid all of the difficulties of an interpretation maybe being right, or maybe being wrong, or maybe being halfway right and halfway wrong, and then trying to figure out what we could possibly use this thing for. This is going a little bit farther upstream and saying, let's just design a system that looks kind of like a black box, but we secretly know it's actually exactly what it's doing, and then figure out if our methods can reliably detect the behavior going on. Yeah, so this is that people are definitely waking up and becoming a little bit more alert to this kind of research angle. Um, there's some interesting broader commentary on this kind of thing. So Chris Ola has this nice figure in some blog post that's like the uncanny valley of abstractions, or this like valley of abstractions with neural networks, where it might be that neural networks start out in terms of their like capabilities. If you're thinking a small network trained on a small amount of data, basically doing a bunch of hacky stuff and using a bunch of hacky heuristics to solve a problem. But as the models get better, and particularly as they solve harder and harder problems, you begin to think, well, their reasoning process, plausibly their reasoning process is going to look a little bit more human, because we might think, well, basically the way you do these math word problems, or the way you do this college biology exam, is just going to require more human-like reasoning, and to rely on some more human-like concepts. So
Right.
there's been this idea that interpretability will actually get easier over time, as the language models, or as vision models develop a more. It's almost, you can think of this like being like the model's vocabulary is like more easily translatable into like a
Hmm.
human vocabulary, or like a human language.
Yeah, yeah. I guess another thing I wanted to pick up on is when you were talking about our just advances in understanding the representations of neural networks. You mentioned that like there was some that we now know that like things are represented as combinations of neurons, and there was some like math research backing that up. Can you say what you were referring to?
Oh yeah, so this was work I'd say from okay, so something that really put this on the map and more the public landscape was Anthropic's superposition work.
Right.
They're like toy models of superposition, where they were able to show that like you could in a given representation space. So if the dimensionality representation space was like 784, which is equal to the number of neurons. So if you had
Hmm.
784 neurons, you could have a model that could actually represent more features than neurons.
Yep.
And immediately this implies that it's like not just a one-to-one map, because it's not just now that one neuron means one feature.
Right. Right.
And mathematically what that ends up looking like is that features are now directions in the latent space, and they're not all orthogonal. So,
Yep.
previously if one neuron was one feature, that's also a direction in the latent space. That's a basis aligned direction. It's just
Hmm.
right along one axis. So features have always been directions, and we've clued in a little bit more to how features are now not basis aligned directions, but they can point in some kind of seemingly arbitrary direction in the latent space. It happens that like if you have 1,000 features and like a 784 dimensional space, these 1,000 features, you can imagine them kind of slightly pushing apart. So like they're all just the right distance from one another. They're all pointing in some
Hmm.
direction, but like they're minimizing potential interference between them. Yeah. So I'll point out that work as something that I think did a good job visualizing this, a good job demonstrating it in toy settings. Um, I would go all the way back to 2017, probably 2017 with TCAV from Google, and this was some work Bean Kim led at Google that
Hmm.
showed that there could be feature vectors in the latent space, and they showed this not really in an unsupervised way, which is basically the way Anthropic showed it, but they showed this in a supervised way. So if you have a data set and you can let's say you're looking for how a vision model represents stripes. So what you do is you have a bunch of images with stripes, and you have a bunch of images without stripes, and you feed all those through the model, and then you learn a classifier on the model's latent space that can classify representations as stripes or not stripes. And with a feature like that and strong enough models, you often see that there's a direction in the latent space that basically measures how stripy something is. And it's not it was never axis aligned or basis
Yeah.
aligned to
Yeah.
begin with. It was always a direction. Yeah.
I wonder. So this actually gets to a methodological question about interpretability. So I remember looking at this TCAV paper and thinking like, well, the thing. So TCAV, it's like, oh, something concept aligned vector,
Oh, I wouldn't even remember
something
the
like that.
acronym.
Yeah.
Yeah, it's
Yeah.
concept activation vectors with a T.
Activation. Right.
So,
Yeah. Something concept activation vectors or something like that. Please forgive
yeah,
us, listeners and Bean Kim.
yeah.
But I remember one concern I had about this paper is that it was kind of trying to understand how concepts were represented in networks. But by concept, it kind of meant like a thing a human thought of, right? Like
Mhm.
we think that there should be some concept of stripiness, so we like have this data set of stripy versus non-stripy things, and we see where that is in the network. And at the time, there's this thought of like, well, there's some danger in um, kind of imposing our concepts onto neural networks or assuming that neural networks are going to use our concepts, right? Like, actually, I think so. You were a co-author on this paper, "Foundational Challenges in Assuring Alignment and Safety of Large Language Models." Uh, Lead author, I guess, was Usman Anwar, and then a
Mhm.
bunch of co-authors. You write this section about just difficulties in interpretability, and I think one of the things you mentioned was like models might not use human-like concepts, and we've kind of learned this. But at the same time, it seems like this TCAF work really did teach us something about how concepts really were represented in neural networks for real. So yeah, on the one hand, I want to say like, hey, we shouldn't like impose our concepts onto neural networks, and we shouldn't assume that they're thinking of things the same way we're thinking about it. But on the other hand, this work that like just did make that assumption turned out to tell us something that like it took the rest of us like 5 years to work out, right?
Mm.
So
Yeah.
yeah, how should we think about imposing our concepts on networks?
Yeah, so that's a good point, and I think this line of research has taught us something durable about how language models or vision models represent things. Uh, yeah, in that longer agenda paper, the foundational challenges paper, um, we definitely criticize this line of research, as much
Yeah.
as much as we can manage. uh, these kinds of methods. So you can think of this as supervised probing and unsupervised probing. So one of the ways that if you so the sparse autoencoders direction that Anthropic and OpenAI and others have been pushing, Apollo as well, um,
Yep.
has been uncovering the same kinds of feature vectors and hidden spaces, but just in an unsupervised way. But so then you need to figure out what they mean. So you don't start with this idea that stripiness is represented,
Hmm.
but you first just find that okay, there's a vector number 1011, and it's a pretty important vector. It seems to play a role in many different kinds of animal classification problems. Um, and so one of the ways people have been interpreting these kinds of vectors is to say, okay, let's look at max activating examples.
Yep.
So we comb through our trained data and figure out what kinds of examples activate this vector strongly. Let's get some negative examples too. We'll comb through the training data, just make sure that, okay, if there's an example that doesn't activate this vector, it doesn't really have anything to, it could just be some other random thing. And hopefully the max activating examples all have some clear thing in common, and the non-max activating examples definitely represent other things and not the thing that the first set had in common. Um,
Right.
so yeah, so what's the issue with all these approaches? It's an art. It's an art.
Hmm.
It's hardly a
Mhm.
science. I mean, you're really doing this interpretative act that is like, okay, what do these examples have in common, and how would we verify that more strongly? It might be that you have something in mind already that's in the supervised case, and the unsupervised case, like text data is really really high dimensional, and it might be that okay, we have 5 or 10 activating examples that are positive examples and 5 to 10 negative examples, and we're going to try to so we basically have like 10 data points, and we're going to try to make a claim about like what one factor ties them all together or what two factors tie them all together.
Right.
This is just a difficult process to get right. Lots of like confirmation bias, lots of data set sensitivity to this kind of thing. Um, yeah, basically saying it's an art and not science goes into a little bit of how it's like we just risk like finding things that we're aware of, seeing patterns in the data that make sense to us, and not patterns in the data that are actually used by the model but maybe alien to us. I'll go into the data set sensitivity thing a little bit, which is there's been some criticism of the TCAP stuff that it's like actually if you use a different data set of stripy and unstripy images, you might get a different vector.
Hmm.
And so it seems like some of these methods are quite sensitive to the data sets we're using. Um, you get similar kinds of data critiques with the unsupervised vector discovery as well. So if you really wanted
Yeah.
to know like what were all the features that my model is using, and what could this feature vector possibly represent. So when I say, you go through the data and figure out what are max activating examples, that literally means you run the model over a bunch of data points and figure out like what are the activations for this feature vector. If you wanted to do this exhaustively, it actually means going through the pre-training data.
Hmm.
It means that you would need to do a forward pass over the entire pre-training data set to be able to say, and this is still just correlational. We haven't even got to a causal analysis yet. But even doing a
Yeah. Yeah.
correlational analysis means you run through the entire pre-trained data set and look for max activating examples. This is prohibitively expensive. So
Right.
now we have this issue where like this feature is going to represent something, but figuring out what it represents is now this huge task. But both in terms of getting the human annotation process correct, and in terms of using the right data to begin with. Yeah.
So it seems like the thing going on here is there's this sort of spectrum of methods where, like, on the one end, you have things like these sparse autoencoders work, which is trying to be like relatively kind of neutral about what's going on in the model. It's still making some assumptions that like this data set is representative and such, but like it's trying to like not impose a bunch of structure. On the other hand, like if you think about TCAV style work, it's kind of assuming that like, hey, The model is going to have a stripy concept. The only question is, where is it,
Mm.
right? And I see this tension a lot in interpretability, where like on the one hand, you sort of you don't want to like add in a bunch of assumptions about how your thing is going to work. But on the other hand, if you don't add in a bunch of assumptions, it's sort of like, how are you validating your thing? You like, you have some method, it has very few assumptions. How do you tell if it worked?
Mm.
Like, do you just look at it and see like, do I like what I see?
Yeah.
How do you think it makes sense to manage this trade-off?
Yeah, so I mean that's a good question, especially because there's so much that's qualitatively different around these kinds of, if you're talking about feature discovery, these kind of probing methods, if it's supervised versus unsupervised, that changes a lot about what kinds of data you need. It changes a lot about how computationally expensive these methods are. So yeah, how can we compare them? Well, one answer is let's figure out what they could help us do, and then just figure out what is best at that. So
Right, right.
so maybe these methods help us do model editing. Maybe it helps us say, okay, here's a feature that is important to the model and it's making some errors on certain data points. So I want to edit how much this model relies on that feature. Maybe I need to turn up its reliance. Maybe I need to turn down its reliance on that feature. Maybe there would be an important feature that's missing from the model, and either there's some you know incredible mechanistic intervention on the model that equips the model with the ability to represent that feature, or I just need to go back and put some data into the training data set and retrain the model so it represents that feature properly.
Hmm.
Let's compare all these methods in terms of usefulness for this thing that we care about, which is like and I can unpack the model editing a little bit. One thing I mean there is just basically making fine-grained adjustments to model behavior. So you've already trained a classifier that maybe handles 1,000 classes, or you have this language model that can do any kind of like text-to-text task. But these things are expensive to train, and they might just make small mistakes. And you just want to be able to fix the small mistakes and diagnose what's going wrong mechanistically, and then fix that mistake. That would be like the model editing application that a lot of this mechanistic interpretability kind of work could be useful for, I think.
Right. Yeah. I guess I'd like to go in a little bit of a more concrete direction. Specifically, you have this, at least a few papers. I see, maybe I'm like reading into it too much to think of it as a line of work, but I see you as having some kind of line of work on just beliefs of large language models. So if I look back, you have this paper, Do Language Models Have Beliefs? Methods for Detecting, Updating, and Visualizing Model Beliefs, by yourself and some co-authors in 2021. 2023, Does Localization Inform Editing? Surprising Differences in Causality-Based Localization versus Knowledge Editing in Language Models, by yourself, Mohit Bansal, Bean Kim, and Asma Gandharayun in 2023. And also like Are Language Models Rational? The Case of Coherence Norms and Belief Revision, by Thomas Hofweber, yourself, Elias Stengel Eskin, and Mohit Bansal, this year. Yeah, what got you interested in just beliefs as a thing to look at rather than representations or, all sorts of other things people do interpretability for?
Yeah, I think it's totally fair to call this a line of work. This has been an interest of mine for a while. So I
Hmm.
think things might seem more coherent if I go backwards in terms of the papers, but the real narrative story is starting
Okay,
from the beginning.
sure.
So yeah, in 2021, um, we knew that models might represent features, and I think people forget how much perception of neural networks has changed over time.
Hmm.
So a lot of people, especially academics in 2019 and 2020, I mean, these things are classifiers. They
Right.
learn features and they classify features. They learn features and they draw a hyperplane in a latent space and divide positives and negatives. And that's what these things are doing. So we want to figure out how important features are to those hyperplanes. That's kind of the recipe, and for a lot of people back then. And then it became increasingly clear that language models store a lot of information about the world. And then it became increasingly clear, basically ChatGPT or LHF models, that language models could converse reasonably about this information in the world. And the picture got a lot richer, and it started to seem more and more that these neural networks were doing something just a little bit more interesting than like storing raw data, learning patterns in data, it seems like they might actually be representing things about the world, and particularly with models that are fine-tuned to be truthful or like fine-tuned to be helpful and
Hmm.
can converse fluently with people about the thing about questions in the world. A lot of people were just really tempted to speak of these systems in totally anthropomorphic terms. I don't think this is always a mistake. It's just really natural a lot of the times to say, like, oh, the model gave me this answer, but like, it knew this thing, but it actually made a little mistake over here. It didn't quite know what it was talking about in this case. And speaking about language models having knowledge about the world really presupposes that language models are representing things in the world and that language models have beliefs about the
Yeah.
world. Yeah. So okay, that's a bit about yeah, why beliefs emerged as like a potentially interesting thing as opposed to simply, features that are used in classifiers. Um
Yeah.
and now, so what is the fascination with beliefs, and why is it so natural for people to speak of models having beliefs or knowledge? Well, I think this has to do a lot with how people explain behavior of agents. And so this is something that we're really interested in the last paper you mentioned, which is about if language models are rational.
Right.
So, and Daniel Dennett has done a lot of work. The philosopher Daniel Dennett did a lot of work elaborating this intentional stance theory, which is it's kind of a folk psychology for how people work.
Hmm.
Um, and it's that people explain behavior in terms of an agent's beliefs and desires. But I think we see this spelled out again and again, between scientific work and everyday situations. When you're thinking about theory of mind tasks and asking someone, okay, why did Sally look for her, I guess I forget what she usually stores in the basket. There's
Right.
like yeah, someone who's like moving a
Let's say
personal
it's
item
eggs.
between like yeah, they like have an egg in a basket versus an egg in a bucket, and if they're out of the room and things been moved from one container to the other, and then they return to the room, where will they look? This is just classic beliefs and desires.
Right.
We believe that someone has a desire to find an object that they own or that they're looking for, and we recognize basically via theory of mind that they have a belief about the state of the world, and these two things combine to produce behavior, and this is just a great way to explain lots of stuff. And Daniel Dennett elaborates what is really a minority view in philosophy, to my understanding, that beliefs are just informational states. So it's a very stripped down view of what a
Hmm.
belief is. And it's basically totally okay to describe beliefs to things like animals and robots, as long as it does a good job explaining their behavior, basically, as long as it
Right.
seems appropriate. Like, clearly, animals have information about the world. Clearly, robots store information about the world, and it seems like if the equation behavior equals beliefs plus desires is a good recipe for explaining behavior, Daniel Dennett basically says, "Go for it. Let you use all the terminology you want to explain
Sure.
how these things are working."
So, can you tell us a little bit just about like what you've done trying to understand beliefs in language models?
Yeah, so this is work that was really led by a philosopher at UNC, Thomas Hofweber, which is I love reading how philosophers write. I feel like it's so
Yeah.
methodical and so clear. It's like, okay, what would it mean for language models to have beliefs? We're going to break it up into three questions. One, do they have the kinds of representations that could be beliefs, or the kinds of representations that are like aimed at truth? And then, when we're thinking about belief and rationality, number two,
Hmm.
do these, if language models have these kinds of representations that are aimed at truth, what would it mean for them for norms of rationality to apply to those representations? So it's like, number one, do they have the representations? Number
Yep.
two, do we expect norms of rationality, norms of truthfulness to apply to the representations? And then number three, how well do language models live up to those norms? And the paper, basically explores each of these three questions one at a time. And some of the core arguments I think are pretty simple. I mean, when we're thinking about models having beliefs, beliefs are supposed to be true. This is like,
Right.
we're not just, so this is in contrast to Dennett. We're not just talking about an information store. We're talking about an information store that exists for the purpose of truly representing something.
Hmm.
So there's this really fun example in the paper that's like, okay, so we know about the Chinese room and dictionaries. You could say, okay, you have a language model, but what if it's just some huge simple shuffling machine and it doesn't really know what it's talking about? It's just whenever you ask it a question, it just does some really complicated lookup procedure.
Right.
You know, it doesn't really know what it's talking about. And you can ask the same thing of, well, a dictionary stores a lot of information. It might store a lot of information about, you know, the city Paris or something, but it doesn't mean it knows about Paris. It's a dictionary. You know, we put the information in
Hmm.
it. And there's this really fun example in the paper that's like, yeah, clearly just having information is about something is not enough. If a wolf walks through the snow, you know, in its environment, and the snow has tracks in it, the snow carries information about the wolf, and a human could read that an animal had gone through the snow. That doesn't mean the snow knows anything. It's just carrying information.
Yeah.
Yeah, yeah. So what is the clear requirement beyond just carrying information? It's aiming at truth. It's aiming at truth. Yeah.
I guess there it seems like there are two things we could say, right? So one is like there's some sort of like criterion of correctness, like is it natural to say that the patterns of snow are aiming at truth or something?
Mm,
This throughout that's taken in the paper you mentioned.
mm,
If I'm thinking of like Daniel Dennett, like expected utility theory style accounts of belief, there it seems like the distinction is okay, like in some sense the snow has a representation of whether a wolf walked through, but it's not using that for anything, right?
mhm.
Like the thing that beliefs are for is you have some like belief like things, you have some desire like things, you combine them to get behavior that that you believe will achieve what you desire,
Yeah.
and like that's the outcome. So it seems like these are two accounts that are like kind of distinct, like maybe in tension. Maybe you could have one without the other. I'm wondering what you think about like which of these we should go for.
Yeah. So let me clarify this kind of like expected utility view. Is that view supposing that, you know, beliefs are basically like information stores that help you achieve your goals? Is
Yeah.
that view? Yeah. Yeah, this view that beliefs are information stores that help you achieve your goals, um, I think does really contrast with this truthfulness oriented view. So I think philosophers have managed as a community to agree that beliefs are aimed at truth, but it's not like an evolutionary account of how beliefs work in people. And it's not an evolutionary account of how all the information stores in our brain work or our own attitudes about our own beliefs. So we might hope for our beliefs to be truth seeking, but actually our beliefs merely help us achieve our goals. And, you know, parts of our brain or parts of our mind will happily distort our beliefs to help us achieve our goals. And
Hmm.
this might be disconcerting to us because we like wanted the beliefs to be truth seeking, but like nonetheless that's what our, you know, brain does, or what that's what part of our mind does, because, you know, that's the job or something.
Sure.
I don't know empirically what goes on. I mean, I guess it's like a mix of a bunch of different stuff, and it kind of depends on the setting. I'm not a cognitive psychologist, but there's absolutely some tension between these things.
So I guess maybe one thought that I have is suppose I just want to understand language models. I want to understand like what they're doing and why they're doing it. It strikes me that the kind of functionalist account of like, well, beliefs are just things that combine with desire like things to produce behavior. That might help me do my job better than understanding, okay, like here's this functional role, but is it aimed at truth, Does it have the right relationship to reality, or is it merely, does it merely have a relationship to what it sees and being useful, like as long as I can use it, like why do I care?
Yeah, so I think the intentional stance equation is like less noisy when beliefs are aimed at truth. So
Hmm.
when you're decomposing behavior into beliefs plus desires, and you're like trying to understand, so then you have like raw data of a system at work where like you ask it some questions, and if it's like truthful and honest, it tells you what it believes, and then you deploy it in an environment, and you see what it tends to pursue. um, the equation is easier to apply and in order to gain like predictive power over understanding what the system will do in different situations. If you can trust that the beliefs are truth seeking and the beliefs are like kept cleanly apart from the system's desires. And we know, so based on everything we've discussed before, I mean, all the mech-interp stuff, a lot of the natural language explainability stuff, um, it's not like you have to have this kind of folk psychology theory of how the system is working. You might just be, you might insist on treating this thing as a machine, and you're going to understand all the gears and levers inside,
Sure.
and forget about beliefs and desires. You know, I want to know what features are represented, and how that feature influences the next feature, and how that feature influences the next logit, and then how that transforms into the model's overall answer to a question.
Mm.
Okay, and let me say one more thing about how these approaches relate to one another. In some ways, I think these approaches are slightly ideologically at odds. I mean, they certainly attract different kinds of researchers with different interests. To a large extent, I think they're totally complementary, because we can think of the mech-interp approach as being at a low level of abstraction,
Yeah.
and you're concerned about what's going on inside the model and how those gears and levers work to produce next tokens. And then we can think of the behavior plus desires work as going on at a much higher level of abstraction. And hopefully these are good abstractions.
Yeah. Yeah.
Hopefully, and this goes back to, okay, yeah, some of the uncanny valley of abstractions work. I think I'm using that phrase correctly. I don't remember the exact title of that blog post or post from Chris Holla. Um, and this is one of our main motivations for working on some of this language model rationality stuff, is asking, are these good abstractions? Could these be good abstractions for thinking about how language models work? Because, and let me give a little bit of opinion at this point, I think
Yep.
we need some higher level of abstractions, and it's really important. It's going to be really important for us to get the abstractions correct, because I both think that like mech-interp right now feels a little too low level to me, and I'm not sure if we're going to be able to fully parse all of the internal mechanisms in these really large and complicated systems, at least not as fast as we probably need to, in order to keep up with safely deploying models. Um, and I really don't want us to fool ourselves into thinking, okay, yeah, here's the system and here's how it works, and it has these kinds of beliefs and these kinds of desires. Um, and don't worry, all of the concepts that the system uses are totally human concepts and very easily
Right.
translatable into human vocabulary. And the system is going to be rational in ways that, like, basically a layperson could expect it to be rational, because the language models are still pretty alien, and they still do weird stuff, like insist on certain reasoning patterns being like why they arrived at an answer, when we for sure know that they're like hiding their reasoning, or the reasoning is hidden and internally or misrepresented by the text that gets produced. Weird stuff is still happening, and I don't want us to fall into there's like two traps. One is like we stay in the low level territory forever, and we never actually gain like a higher level of abstraction and predictability in the systems that is able to like keep up with it, I think, where like capabilities progress is going. And the other trap is like we really treat the systems as way too human like and way too rational, and then we forget actually how alien they are.
So this actually gets to kind of a question I have about like how we figure out model beliefs. So one way you could do this, which I sort of see is represented in the R language models rational paper, is to say, okay, a model's belief is just whatever controls like what it says in a somewhat straightforward way, right? If whenever you ask a model like, is Paris the capital of France? If it's the case that whenever you ask it that, an answer is yes, then you might want to just methodologically say, okay, that's just identical to saying that it believes that Paris is in France. But I think you might also have a different perspective where you're like, okay, maybe models just have some underlying beliefs, but they're not totally straightforward in how those beliefs translate to what they say. Like maybe they're speaking strategically, maybe they're like willing to lie. So like they actually think that Paris is the capital of Italy, not France, but they just know that you're gonna like make a big stink if if the language model says that. So that's why it says it's the capital of France. Um, I'm wondering, yeah, these strike me as kind of different ways of understanding language model beliefs. How should we? Which way should we go?
Yeah, this is a good question. It's a really tricky problem right now. Yeah. I think the direction we go in the paper is trying to make a lot of assumptions and then give some basic formulation for what beliefs would look like and how they'd be expressed. So the assumptions are that the system understands what you're asking and is trying to be truthful and honest, and it's really playing along. It really is cooperating. And one of the very first assumptions we make in the paper is that models represent things about the world. I mean, this ongoing debate between, some of the Bender crowd, and then there's like a Piantadosi. I probably said that wrong, but it's Piantadosi and Hill, Felix Hill paper is more of a conceptual roles kind of view of meaning and language models, which is much more charitable to the idea that language models are actually representing about the things in the world,
Hmm.
representing things in the world. That's one of the very first assumptions we make in the paper is that
Right.
language models are representing things in the world. They seem like competent speakers in important ways. They seem to understand what we're asking them a lot of the time. So if they're also trying to be truthful and honest and capable of reporting what they would believe, then what you do is you look at the probability mass on like yes tokens and you look at the probability mass on no tokens in response to a yes no question. And you basically treat what the model generates. We're going one level below that, just in term, rather than just what it generates. We're looking at probability mass and all kinds of affirmations to a yes no question, and saying, yeah, if you met all those criteria, this seems like a reasonable way to say like the model assents to the question that you asked it. But things just get a lot thornier from there. I think for reasons you describe. In the 2021 paper, which introduces some of the belief terminology and really is largely focused on model editing, we take a slightly more expansive view, less formally, but more expansive or ambitious in scope in terms of what a belief should count as. So, one thing we're looking for there is logical consistency. And this immediately opens up a lot of issues for language models
Right.
because they're definitely really knowledgeable and they're like decent at a variety of logical reasoning tasks, but they're just going to say stuff that conflicts sometimes. And if you ask, okay, what are all the consequences of Paris being the capital of France? Something that should be a consequence of Paris being the capital of France, the model might not actually agree with, or the model might say something to the contrary. And then it's like, okay, well, if the model contradicted itself, like, so basically in that 2021 paper, we're pointing out that this seems like a criterion people would be interested in. Like, if you want to know if a human really believes something, yeah, you like ask the question one way to them, and then you might ask a bunch of related questions just to make sure that they like really understand what you mean and they really understand what they're talking about, and they've kind of considered some basic consequences of the things they're espousing, such
Right.
that they like, yeah, they really do basically know what they're saying and stand by what they're saying. And so what happens if you catch some really basic, silly logical discrepancies, content knowledge discrepancies in the language models? What do you conclude then? Well, maybe it's like the language model is like not really like an agent. Maybe it's like modeling a bunch of different personas or like modeling a weird combination of agents from the pre-training data. And like it's doing this thing that like you ask the question one way and it knows like you want the kind of answer that like an educated liberal would give, and then you ask the question a different way and it's going to give like the kind of answer that like a conservative domain expert would give to the question.
Hmm.
So like it seems like it said something inconsistent, it seems like it doesn't have a coherent belief, but it's actually doing something even more complicated than that, which is like modeling what other people would say in response to your question. I mean, that's that's nowhere near the end of the difficulties in terms of like, yeah, really getting at the underlying what does the model believe question.
Yeah. I wonder if this is a way of thinking about the criterion of beliefs being aimed at truth. So, like, suppose I take a very functionalist account of what it means for beliefs to be aimed at truth, which is to say that there's some reliable process by which beliefs tend towards the truth, right? That gives me a way of sort of nailing down which things count as beliefs, right? like if I because if I'm just inferring beliefs from behavior, I worry like, well, does the model like believe this thing, or does it have like some unusual preferences? Like it's really hard to disentangle belief from preferences. People are interested in this. There's this thing called Jeffrey Bulker rotation, which like kind of interesting to look up, just about how you can like change your probabilities and your utilities, and like
Oh yeah,
you act just totally the same.
cool, cool.
But if we say but if we say the beliefs have to be kind of accurate, then that kind of fixes the what counts as your beliefs. Like it gives you a it lets you like pick a thing from this class of things you're sort of unclear of how to choose between.
Mm.
Yeah, I'm wondering what do you think about that, just as a strategy for getting at beliefs in
Yeah,
language models.
yeah. I really like this line of thinking, because one of the things you might be able to test here empirically is you say, okay, we're looking for kinds of information stores in the model that are truth seeking. So let's give the model some data and figure out what its behavior looks like, and then
Hmm.
okay, yeah. So we have some behavior and environment. It's still often just really hard to parse what are the differences between the preferences and the desires, and what are the differences in the beliefs. So well, we've given it some data. Now let's give it more evidence for various hypotheses and see how it updates.
Yeah.
And see, okay, so like if this information store is actually truth seeking, we know with this amount of data, the model behavior should look like this. And with additional data, and if the model understands the state of the world better, then the behavior should change to this other thing. And you might be able to, I think you can design some experiments like that where if you can fix the desires or makes assumptions about the desires and then vary how much evidence the model has about the world, you should be able to see, is the model like, in what way is the model learning more about the world, and how does that
Hmm.
influence the behavior, and then start to actually identify some of like how truth seeking it is in different regards, versus like maybe there are certain things about the world that it's like totally just using in an expected utility way, and it's totally just instrumental how it relies on that kind of information. So that's a little abstract. But I think
Yeah.
it's like, yeah, there's like some unknown variables, and you need enough data to actually be able to identify all the unknown variables. Um, what makes this strategy still difficult, uh, I think, is that we don't know yet how language models incorporate new information. We don't know how
Right.
they respond to different kinds of evidence. We don't know what they treat as evidence. So there's so much I think that we can take for granted when we're studying, you know, animals and humans,
Hmm.
that it's so hard to even begin applying these to language models, because like, yeah, we want to run studies where we can treat them as agents, but like there's so many ways in which it's hard to exactly know it's like a rational agent. It might be like this, like I said before, it might be this weird amalgamation of different like agent simulators. It might be like, yeah, it might be a perfectly truth seeking agent, but like it just has really bad uh practices for interpreting data about the world. And we're just trying to communicate certain things to it, and it like doesn't know how to update its beliefs rationally over time. And this just leads to really wonky behavior and experiments.
Yeah. And interestingly, like, so I genuinely didn't plan this, but this is sort of thinking about beliefs. Like this is kind of just copying the structure of the paper. Are language models rational, right? Like half of this paper is just about coherence norms. Like beliefs should be coherent with each other, and this kind of gets this is really related to your paper. Like, do language models have beliefs? Where you say like, okay, you have a belief if like it's kind of coherent with some other beliefs, and like,
Hmm.
if this implies this, you change the belief here, it should change the belief here. If you like edit the belief here, that should produce a result here. And then talking about like giving language models evidence, sort of gets to this part of our language models rational of like belief revision. And yeah, it just says like, yeah, it's difficult to understand how things get evidence, but like if you could, this would be related to rationality norms.
Yeah, so I think earlier when you said this is a line of research, yeah, absolutely, because we've got one more thing coming on
Hmm.
this. Yeah, the straggler project from my PhD is going to be one more paper that will hopefully offer a lot of criticism of the model editing problem and belief revision problem in language models,
Right.
and try to make it clear how difficult it's going to be to actually properly measure belief revision in language models. And hopefully eventually help people better equip language models with the ability to do that. I mean, we certainly want to be able to edit individual beliefs in language models. It's just going to be a little harder than for all the reasons we've been discussing. It's going to be a little harder, I think, than people have given it credit for so far.
Yeah. And actually, this gets to a paper that you have been able to publish. So,
Mm.
does localization inform editing? Yeah, can you tell us a little bit about what you found out in that paper?
Yeah, absolutely. Yeah, so basically, we were very surprised by the main interpretability finding in this paper that past work had pitched some model editing methods. Again, you're trying to update factual knowledge in a model. Past work had pitched some model editing methods and motivated these methods based on some interpretability analysis that they'd done. So there have been some claims. This paper was not the only paper to make such claims.
Right.
Many people have this very intuitive notion that uh, where information is represented in models should tell you where you should edit the model in order to adjust its behavior, its answers to questions, so on. Yeah. So this in this setting, they were looking at updating knowledge in models, and yeah, they ran a kind of interpretability analysis. The
Hmm.
work we were building on was this work on Rome from Kevin Meng and David Bao and others, and they used a kind of interpretability analysis called causal tracing, which aims to identify certain layers in the model that are responsible for its expression of knowledge and the storage of knowledge. And so they make a really intuitively convincing argument.
Hmm.
If the knowledge looks like it's stored at layer 6 in a model, and you want to change what the model says in response to a question,
Yep.
like where is Paris? What country is Paris the capital of? You should edit layer 6.
Right.
That's where it's stored. So go and edit that layer, and that'll help you change what the model says in response to questions about Paris. You know, very very intuitive argument. And then they develop a method for doing this model editing that was really successful and like a huge improvement over prior fine tuning and hyper network or learned optimizer based approaches. Their method
Hmm.
was focused on really low rank updates to certain matrices and language models, and it was heavily inspired by this linear associative memory um, theory, linear associative memory model from computational neuroscience. That is like a model of how matrices can be information stores or memories for biological systems. The method worked great, and the empirical results were really good, and the story sounded great. And we did not initially set out to like try to verify the interpretability result here, but that is where this project went. So so we noticed that sometimes the causal tracing method, the probing method, suggested that knowledge was actually stored at later layers.
Hmm.
They make this claim that knowledge is stored in early to mid layer MLPs and transformers. We just noticed everything replicated fine. We just noticed that 20% of the time the knowledge seemed to be stored at later layer
Hmm.
MLPs. And so we were like, oh, that's weird. It seems like there's some free lunch here, because if 80% of the time it's stored early on, you should edit early layers 80% of the time. And then if you ever notice that it's stored in later layers, you should edit the later layers. And this isn't actually how the editing results look empirically. It's always better to edit earlier layers than the later layers. The method's much better editing early layers than later layers in terms of adjusting the knowledge in the model. The main contribution of the paper is to look at the data point level. Do the causal tracing results tell you where you should edit? If the causal tracing says it's stored at layer 6, is layer 6 the best layer to edit? If causal tracing says it's stored at layer 20, is layer 20 the best layer to edit? And the surprising thing to us was that the correlation between the localization results, that's the causal tracing results, and the editing performance was just zero. It was just
Huh.
zero. Yeah. Yeah. There was just no relationship between the localization results and where to edit.
That's very strange. Yeah. What do you make of that? Just like, what does that mean?
Well, we certainly spent a lot of time racking our brains about it. And something that was helpful actually was talking to a couple people. I would say 80 to 90% of people were pretty surprised by this result. And then like 10 to 20% of people were just like, oh, yeah, I mean, I don't know. I wouldn't have expected language models to do anything like localize information in specific places, or like, I don't know, fine tuning is weird.
Right.
Yeah. So actually, some people weren't that surprised about it, which was helpful for like breaking us out of the mold.
Mm.
So what we came to through all of our discussions was that we're guessing residual layers play a pretty clear role here. And I think this is another big, let me say, object level win of interpretability research over the years, is that we've been able to gain a lot of insight into how information accrues over time in the transformer forward pass. So when language models consist of these, stacked layers, stacked attention and NLP layers that compose a transformer, and between all the layers there are these residual layers. A lot of work in interpretability has been able to show that like a representation across layers like slowly approaches some kind of like final state, where like the final state is the state that is useful for like answering a question or like predicting the next token. But if you like look across layers, it's just very gradual how information gets added to the model, or to the hidden states. Sorry, over the course of the model forward pass. And this basically leads us to believe that. So let me point out one empirical thing that will suggest, I think, our final conclusion so far,
Mm.
which is that if the knowledge seemed to be stored at layer 10, you can often do a good job editing at layer 5, or editing at layer 15, or editing at layer 10.
Huh.
So you can, if you're thinking about inserting the information into the model forward pass, it seems like you could insert the information before or after this particular place where some other information is represented. So this gives us the sense that what you're doing is just adding to the residual stream. Like information's just flowing. You can drop some new information in wherever you want.
Right.
That's the clean picture. I mean, it's speculative.
Sure.
We had a reviewer we had a reviewer ask us like, "Oh, like this discussion section, can you run some experiments to do that?" And we were like, "Well, there are no good language models that don't have residual layers." So yeah, and the big caveat here is that, and here's the real tension. There's a really interesting paper that is looking at BERT. So this is a model from a few years ago. It's a paper from a few years ago.
Yep.
Basically, the whole point of the paper is to look at what happens if you swap layers. It's like how commutative are layers in a model.
Mm.
And people read this paper very differently. But I can give you some numbers. It's if you swap two adjacent layers in a BERT model, which could be like a 12-layer model or an 18-layer model,
Right.
performance on an NLP task might drop by like 2-3%.
Okay.
And if you swap like really far, like if you change the first layer and the last layer, its performance will crash like 30% or something.
This is like 30 percentage points of accuracy.
Yeah, 30 raw points off of like 80 or 90 or something.
Okay.
People really read these numbers differently. So some people have looked at these numbers and said like, wow, layers seem surprisingly swappable. You could swap two layers and like only lose 2 points or something.
Mm.
Some people, I'm probably in the latter camp, are like, 3 points of accuracy. I mean, for a lot of, for years, that's been a publishable result. That's been like a big deal in various settings. It's like, you've really found something if you're changing accuracy by 3 points.
Right. Right.
Yeah, layer roll is important. And it seems totally weird that you could inject information into layer 5 versus layer 15 and like have it have the same effect on the, surely there is dependence on like the information coming in to layer 7 and then layer 8 and layer 9. That's the tension here. We really don't have a complete picture, but there's been a lot of cool mech-interp work here focusing on, um, yeah, particularly I'll mention Morgeva. That name is Morgeva. Has
Mm.
been doing a lot of work looking at how this information accrues over time in the model forward pass, and also recently how this information enables models to answer factual questions or do some simple kinds of factual associations. So we're gradually gaining a bigger picture there, which, maybe will one day help us design better model editing methods. Because yeah, that's still kind of the goal here. We mentioned this before. This was certainly the goal in the Rome paper, and I'm still optimistic about this. I'm hopeful that we're gonna be developing our own better causal models of how the neural networks are working. That I'm optimistic. It will eventually help us actually do some model editing. It will eventually help us like tweak, some internals and change the behavior.
So that was kind of I guess, a hopeful read of like, oh, here's a way we can make sense of the results of this paper.
Uh, uh,
Like, one thing, when I read your paper, one thought I had is like, okay, we're working off this assumption that belief localization kind of is a thing, right? Like beliefs are stored in one bit of a neural network such that we could say, oh, yeah, here's the bit, we found it. It doesn't seem like that has to be true,
mhm.
right? And I wonder if I had this method that purported to tell me where a belief was localized in a network, and I have this new thing which is like, oh, but if I'm editing a network, I have to like change it somewhere else. One way I could think of that is, oh, I just proved my assumption wrong. Like we just demonstrated that it's not actually true that there's one place where
Yeah.
the this knowledge resides. Yeah, what do you think of this interpretation? Am I like being too paranoid or too skeptical here?
No, this is a good point. I think skepticism is completely warranted. You had this comment earlier that we interpretability. A lot of the progress actually seems to be like disproving naive models of like
Hmm.
how language models or neural networks work, and I think this is a good example of that. Um, and really, the next step here is to start developing some better causal models of what's going
Right.
on. Simply the idea that information is localized is this like very simple, intuitive, potentially naive mental model of how things work. And yeah, we've probably disproved that. And like I said before, 10 to 20% of people I talked to about this were just not surprised at all. So like they already had some kind of working mental model
Yep.
of how the transformers would work. Yeah, what next? We should figure out what components are necessary for achieving a certain behavior. We should figure out what components are sufficient for achieving a certain behavior. We need to start drawing some like actually more complicated causal pictures of, okay, so this layer represents this information, and then it passes that information to this other layer, which applies a function to that information. And then you get a new variable. And then the next
Right.
layer reads off that information and actually just all it does is it reads it off and changes its position. And so it puts it in a new spot. And then the layer after that reads from the new spot and decides how that information should combine with some other information. And basically this is saying we need circuits. We
Sure.
need to build up a circuit understanding of how the information flows through the network. And yeah, this picture that was like, okay, there's a feature here, and here's how it relates to behavior. There's information here, and here's how that relates to behavior. Was just way too high level, and we
Right.
need to start actually drawing a much more detailed picture, which is like the complete end to end story. I think.
So actually, while you were saying that, an idea occurred to me about like another kind of like simple localization model that may or may not be right, that you might already have enough information to shoot down.
Hmm.
So here's the thought, right? I think sometimes, especially in the like transformer circuits line of work by Anthropic, Chrysola et al., I think some I think in that work there's this thought that like the residual stream is the key thing. This also relates to what you were saying. The residual stream is some kind of key thing. And maybe a thing we can do is we can interpret sort of dimensions within that residual stream, right? Maybe there's like one dimension within the residual stream, or one direction inside the residual stream that really is like where some knowledge is localized in some sense, but it's localized in a dimension in the residual stream, not in a layer of the network.
Hmm.
I think, and let me know if I'm wrong, I think if this were true, then it would suggest that, like, yeah, you know, any layer of the neural network you can edit to change the model's beliefs about a certain thing. And it doesn't really matter which layer you edit, but whichever layer you edit, like the edits should do a similar thing to the residual stream. I think that's a prediction of the like residual stream direction theory of
Hmm.
language model knowledge. You might already know if that holds up or not. Does it hold up? And am I even right to think that this tests it?
No, no, I like the sketch. Yeah, so I think there's been more work looking at interventions on weights versus interventions on representations for
Hmm.
one here, where you could, which is maybe a little bit more direct path. So I don't think the exact experiment you described has been done, but certainly when people are thinking about um, a certain direction encoding for some knowledge or a certain direction in coding for a specific feature and just how highly that feature activates,
Yep.
that immediately suggests, okay, let's just turn that feature up or let's turn it down. Let's clamp it to a certain value. Let's do some intervention at every layer, at a certain layer, so on, um, and see the effect on behavior. And this is a good causal intervention for actually understanding, like, if that representation represents what you think it's representing, and
Hmm.
testing that a bit. And then, yeah, the useful thing here would be like editing it. So if it was like faulty in some way or malfunctioning in some way, you would change it. And it's a very direct route because you're just editing the representations. The the first kind of odd thing about this is like, well, we would just like to be doing an intervention like on the model. Like we
Hmm.
want to be intervening on the model such that we're like permanently changing the model's knowledge, or we're permanently changing how the model processes information. Like, yeah, I can always clamp a representation, but like nothing changes after that on other data points. Like I can't always clamp this representation for every data point, obviously.
Right.
Yeah, I mean, I like the idea that testing, like, okay, so let's say we're going to try to edit the weights to adjust that knowledge. Presumably, the hypothesis there is like when we edit those weights act on that mechanism. And what I mean
Yep.
is they upweight or downweight that feature, and that's how the ultimate behavior gets changed. What I think is more elegant about your sketch and this kind of like weight intervention thing, or potentially just there's something that's just like appealing in terms of like generalizability or universality of this kind of like weight intervention thing, is like
Right. Right.
when you edit the representation, you're kind of starting in the middle of the process. You're like, well, the model acts upon representations and that leads to behavior.
Hmm.
So you if you start in the middle and you say, okay, let's clamp the representation and see how that leads to behavior, it's like, well, great, that's a hypothesis that you might be able to verify. But it's not actually the whole causal chain. The whole causal chain is that the input comes in and weights act upon the representations, and then representations are processed by other weights, and then there's logits, and then there's behavior. And and if you can actually adjust the weights, yeah, not at that point you're getting, I think, a larger slice of the causal pipeline, and you're doing something that it can be permanent. You can permanently edit the model
Hmm.
such that it changes its behavior on one example, and then hopefully you would want to check, you know, not others that it's not supposed to change its behavior on. And also, to tie back in the consistency among beliefs things, if you're like editing some knowledge, there is other data that its behavior should change on that you would want to check. That this activation clamping thing, I think is maybe just not the right exact method for.
Yeah. I mean, I think people do. I do hear about people like checking this sort of thing with activation clamping.
Mm,
I'm also thinking like steering vectors. So like Alex Turner's
yeah.
work, you have some steering vector um for some property. Like if I give it some examples, does the network like generalize to other things where it's supposed to have
Mm.
this property? Yeah, there's. I sorry, I'm being a little bit abstract. Unfortunately, like the concrete thing I'm thinking of is like unpublished work that he's kind of discussed. So
Yeah, yeah. No,
I'll,
no,
I'll
that's
talk I'll
definitely
talk about it after the recording's over.
sure.
But
Okay.
I think there is some work kind of like this.
Yeah, and I am still. I mean, there's so much work in this area nowadays. It's hard to keep up everything. But like the inference time intervention
Right.
paper does something that's kind of like permanent activation steering. You're just kind of like permanently upweighting some activations that are supposed to be truthfulness activations. And so it's like, yeah, we want all the data to be answered truthfully, or like all the questions to be answered truthfully. So like it's fine that we've just permanently upweighted these activations via, some. And actually, I don't even remember the exact implementation detail there. You can think of, well, I'll stop there basically. Yeah, but yeah, I definitely remember some other examples that look at this kind of generalizability thing, and I think the right way.
Sure. I like to move out a little bit just talk about beliefs in neural networks. I think, well, and this might be a little bit out of your wheelhouse.
Mm,
Mostly, I think when people, especially in the public, think about language models or think about neural networks being like smart, being intelligent, having beliefs, I think they're normally thinking about language models, right? It's
mm,
not so obvious why we shouldn't think of other kinds of networks as having beliefs. So like the simplest case is like if you think about AlphaGo, right? Like reinforcement learning playing networks, like plausibly they have some sort of beliefs about what moves work. I'm also thinking of image generation models or movie generation models, right? These are things that like they're generating some scenes in the world. You might think of them like it's very tempting. Like if you prompt one of these models to say, "Hey, please like show me a video of the cool sights in Paris," and it shows you a thing of something that looks like the Eiffel Tower, one might be tempted to say like, "Oh, this image or this video generation model believes that the Eiffel Tower is in Paris," right? I'm wondering, are you familiar with the work on like inferring beliefs of things other than language models? And does it look similar, or do we need to do different things?
Yeah, this is really interesting, and I can say my first reaction to this is like I'm pretty sympathetic to describing a lot of these um, systems, like image generation models, video generation models,
Hmm.
RL agents, as having beliefs. Yeah, I think one of the first stumbling blocks there is that people normally think of beliefs as being expressed in language, and
Right.
philosophers think of beliefs as being expressed in some kind of formal language that might then like map noisily to natural language,
Hmm.
but like is expressible at some level of formality. And I think what would make this case compelling for like an image, let's say a video generation model, um, having beliefs is for it to be able to generate some scene that demonstrates some knowledge about the world.
Yep.
And then if you could actually translate its internal representations into a sentence that expresses that knowledge, you'd be like, oh, okay, yeah, definitely it like knew that thing. Like, when the model generates like a ball being thrown and it like seems to have some intuitive physics, and if you could actually figure out how to translate its internal representations into like a sentence that describes like how you might expect a thrown ball to move through the air, you'd be like, ah, yes, okay, this was just like the last step to showing that like, yeah, the model actually kind of knows what it's talking about. And I think that colloquialism actually is important because it's like, yeah, knows what it's talking about. You're like able to express like what the thing is.
Hmm.
But it doesn't mean that the representations just don't already act as like truth-seeking representations. Again, that being that criterion, like truth-seeking, like an information store that is aimed at truthfully representing the world. I think there's a lot of representations and like all kinds of multimodal models, all kinds of RL agents that aim to represent things truthfully.
Actually, one thing I'm thinking of, so you mentioned there's this difficulty, which is like, how do you translate it into a sentence?
Hmm.
I think there are two thoughts I have here. So the first thing is like, in some ways, it's a little bit nice that like language, like neural networks, they don't necessarily use the same concepts as we do, right? As you've written about, as you've noted. And so on the one hand, I'm like, okay, it's kind of nice that we that by being a little bit removed from natural language, just a little bit, like maybe this helps us like not be too shackled to it.
Hmm.
And then on the other hand, like if I look at your work, like the do language models have beliefs, detecting, updating, visualizing beliefs, we're sort of using these like implication networks of, if you edit this belief and, this implies this, then that should change to this, but it shouldn't change to this. It strikes me that you could do something very similar with, let's say, video generation models, right?
Hmm.
Like somehow it seemed like it used language, but didn't really. Like imagine, you want to persuade a thing that you want to intervene on some video generation model and get it to think that the Eiffel Tower is in Rome but not in Paris. So here's what you do: you like try and make some edits such that you generate a video like, hey, show me a video of the top tourist attractions in Paris, and it just has the Arc de Triomphe. It doesn't have the Eiffel Tower. Show me a video of like the top tourist attractions in Rome. Does have the Eiffel Tower. Show me a video of the top tourist attractions in London. Shouldn't change anything. Like this seems like a very close match to work you've already done. Now, I could be like missing something important, or it's probably like way more annoying to run that experiment because like now like Now you've got to watch the video and like somehow you've got to check if like
Yeah. Yeah.
does it look enough like the Eiffel Tower? There's some difficulty there, but it seems like some of this natural language work actually could translate over.
Oh, absolutely. And I like what the kind of cases you're setting out. I mean, I think it's almost directly
Hmm.
analogous in a lot of ways. Yeah, you could run that experiment. It sounded like you're kind of imagining like a text to video model, which I think that makes that experiment a little easier to run. But yeah, for sure. The setup makes sense. There's a paper that comes to mind that I unfortunately won't remember the name of, but they were trying to do some editing with vision models. And this was an earlier paper, I think, before
Hmm.
people had this more grand view of what editing could accomplish. And it's like, wow, we're really changing the knowledge and the models, or we're trying to, at least. And it was a little bit more in kind of the feature to classifier pipeline sense, where it's like, okay, the neural network as a classifier uses features. We're going to intervene on what features are represented. And this paper did something that was, it was like changing how the model represents snow, I think. So like there'd be a data set where like snow is statistically related to a variety of classes,
Hmm.
and the model learns that. um, and they wanted to do some intervention that would like lead one class to like usually get classified as another, by virtue of there being snow in the image, or by virtue of there being not being snow in the image.
Okay.
That was their goal for editing.
Do you remember the authors?
Editing a classifier by rewriting its prediction rules.
Okay.
Yeah, so far people have been thinking about this in other modalities as well. I'm sure there's work in RL setting where, unfortunately, not all of, I think, subfields and AI communicate that well with each other. There's a lot of work that I think is like actually super interesting interpretability work that goes on in Vision and RL that just doesn't get branded that way.
Yeah.
So it's like hard to find sometimes. But yeah, people train RL agents and then are doing all kinds of interventions on them nowadays, like changing things about the environment, changing things about the policy network itself, to like try to better understand what factors lead to what behavior. And a lot of that you can think of like editing, like model editing, like editing a goal of the agent, or like editing how it perceives its environment.
So moving out a bit, I think maybe on your website, maybe somewhere else, I've got the idea that there are three kind of lines of work that you're interested in. So the first two are interpretability and model editing, and it seems like we kind of discussed those in the previous discussion. The third that I've heard you mentioned is scalable oversight. I take to mean something like figuring out how we should supervise models, how we can tell if they did things that were good or bad when they get like significantly smarter than us.
Mm.
In my mind, this is like the odd one out of these three. Do you agree? And like, or do you see there being like some unifying theme?
No, I think you're right about that. It's a recent new area for me.
Yeah.
I've really stretched to them together in talks before, where I've
Okay.
said like, okay, model editing is about trying to control model behaviors when like you have a expected behavior in mind, or like you can like properly supervise the model.
Right.
And scalable oversight, or easy to hard generalization, is about trying to develop, yeah, this kind of predictable control over model behaviors, but in a setting where you don't exactly know how to supervise the model. Yeah, but it's extremely like it's like a segue for a talk. It's not like a very deep connection.
Well, I do think there's something to that. Often people talk about inner and outer alignment as being like somewhat related but distinct, and interpretability has this relation
Mm-hmm.
to inner alignment. Scalable oversight has this relation to outer alignment. I think there's something there, but it sounds like this isn't like how you got interested in scalable oversight. So how did it become one of the three?
Well, you're right, because it's not the original story behind the research we've done in that area. Originally, we were really interested in some of this work on eliciting latent knowledge.
Hmm.
That there's been some blog posts in the area. There was a research paper from Colin Burns and others at Berkeley on this problem, that we were very interested in, largely from an interpretability perspective,
Right.
understanding how to probe and detect knowledge in language models. Um, but then I realized after reading and rereading Colin Burns' CCS paper, um, that it was really about scalable oversight, and it really wasn't an interpretability thing. The
Hmm.
problem that they were primarily interested in was uh, getting models to report their knowledge or extracting knowledge from models,
Right.
even when you don't have labels, even when you can't supervise or fit the model to a data set or probe it in an unsupervised way.
Hmm.
How this came to my attention was we're really looking into this closely when I was working at the Allen Institute for AI last year, doing a research internship there with Sarah Wigreff and Peter Clark. And so we were looking at the CCS paper, and then we realized it was really about scalable oversight,
Yeah.
which wasn't. I think that was immediately clear to a lot of people. It wasn't immediately clear to us because it was also written in this kind of interpretability language
Hmm.
at times too. And then the first thought we had was, well, it's not like we don't have any labeled data. We have some labeled data. Like it's just like we're trying to solve problems that we don't have labeled data for. But there's labeled data everywhere. There's just like all kinds of labeled NLP data that we have, all kinds of data sets that are just specifically constructed to like contain true false labels for claims about the world. Um, shouldn't we be leveraging this to like fine tune models to be truthful or like extract knowledge from models? Um, so what really is the way to set up this problem?
Yep.
This turned into a paper we worked on called like the unreasonable effectiveness of easy training data for hard tasks, which in a lot of respects looks a lot like OpenAI's weak to strong paper. And there's just some interesting kind of close analogies between them. Yeah, the setup is you want to do well on a problem that you don't know the answers to. And you can supervise the model on some problems, but not the problems you really care about. And there's some methods work in their paper. Our paper is really just focused on kind of benchmarking and getting a lay of the land. We
Yep.
just wanted to try to gather data. Like it could be like STEM questions, it could be like math word problems, it could be like general knowledge trivia. We had some kind of various tasks like that,
Hmm.
and divide the data into easy and hard, and pretend that you can't label the hard data. Pretend that you can only label the easy data, and fit a model to that, prompting, fine tuning, probing, whatever way, fit a model to that. And we're just doing some kind of benchmarking where we're asking how that was a little bit of supervision. It wasn't the right supervision, but it was a little bit of supervision. How effective was that supervision?
Okay. And should I think of this as kind of modeling humans giving feedback to like we're doing RLHF plus plus on like, CEO bot. We're training it on like problems where we do know what the CEO bot should do, and we're hoping that it does well on problems, that where we don't know what CEO bot should do. Is that like roughly the kind of picture I should have for what this paper is trying to be a kind of toy model of?
Yeah, so that's an important question because it's like, yeah, okay, what does this lead to? We want to have some calibrated judgment on when there are problems where we really don't think we're going to be able to supervise the model effectively.
Hmm.
And let me quickly drop in an example from the Amadei paper et al. Concrete problems in AI safety that I think is the one that basically introduces this terminology scalable oversight. We're thinking about a setting where like the model might be acting in an environment where it's taking large complex actions, and we just can't check everything. We just can't check every possible case. So we can't properly reward the model based on like if it's done a good job or not all the time. And I think the CEO analogy here is like, yeah, the model's doing like complicated things and like a complex environment and a long time horizon, and we just can't properly like reward or penalize the model all the time. So right, yeah, backing up, we want a calibrated judgment for, okay, well, if we can properly supervise the model on some things, how should we expect the model to behave on the other things that we can't supervise it on?
Right.
I'm really excited about more methods work here for trying to, if there's a gap there, if there's a supervision gap, I'm excited about ways for trying to close that gap. But whether we get it, whether in terms our easy supervision or our weak supervision is like 60% effective or 70% effective compared to if we could like get the proper supervision for a problem in place.
Hmm.
Getting that number from 70 to 80% is good. That's like interesting methods research that should be done. But up front, we just want to know what the number is. And
Right.
and we just want to be able to say like, if we think the supervision is like halfway effective, are we comfortable deploying this agent in a setting where like it's sometimes going to be doing things that we never actually checked if we could do it properly or not, or we don't even know how.
Right. And just to kind of concretize that, by like halfway effective, 60%, you're thinking just like in terms of the gap between an unsupervised model that like hasn't been trained on like any instances of this problem versus a model that's been trained on like the right answers um to the hard problems.
Oh yeah,
Like
thanks.
is that the gap you're talking about?
Yeah, sorry. Thanks for clarifying. That is the gap exactly. And that's the gap in our paper where I mean, terminology is not important here. We're calling it easy to hard. Um, where the baseline is you have some system that you just can't supervise at all. So that might look like zero shot prompting. You haven't. It might look like a totally unsupervised method. It might look like CCS or an unsupervised probe where you have questions, you have data, but you don't have labels for anything.
Yep.
The ceiling is you can fully fine tune the model, you can fully probe the model with labeled data for exactly the kinds of problems that you care about. And then the question is between that baseline and that ceiling, how far can you get with incomplete supervision? Yeah,
Sure.
yeah, that's our setting. A small technical detail, a slight difference with the weak to strong setting and some of OpenAI's work is that their baseline is like the weaker teacher model trying to do the problem on its own. So they kind of have this analogy to like people and like a super intelligent system where like we could either imagine we try to do the problem on our own or we try to align the super intelligent problem to do it for us. So like their baseline is like a person doing a problem on their own and their ceiling is like a fully aligned super intelligent system. And then what's in the middle is like us weekly supervising the super intelligent system. And so it's kind of like the baseline's different there. I think this is actually important to think about a little bit because we're just going to have like options for baselines. I
Yep.
mean, it happens that a lot of the time pre-trained language models do decently at stuff zero shot, which is kind of surprising.
Yeah.
Sometimes pre-trained language models do better at things zero shot than lay people do. So if you're thinking about accuracy as a metric, um, the layperson is a weaker baseline than the fully unsupervised model. That's how we ended up with our baseline. The story I just gave is how they ended up with their baseline. Yeah, yeah, but the gap is the gap.
Yeah. So I actually have a bunch of questions about just how we're measuring things, what the methodology is. But before we get to that, I think listeners are like chomping at the bit. They want to hear what's the gap? How much of the gap can you
Oh
recover?
yeah, yeah. Uh, on a lot of our tasks that we were covering, like it's like 95% or like 97% as effective. So let me make that concrete. If you were solving eighth grade STEM questions and
Hmm.
supervising a 70 billion parameter language model with third grade level supervision, um, it does just as well as if you were supervising it with eighth grade level supervision. If you were testing on college STEM questions and you were supervising the model at a high school level, it's going to do just as well as if you had supervised it with the college level supervision. There are a couple places where the gap starts to grow and the effectiveness of the incomplete supervision starts to become clear. One of the settings was something a little bit more like reasoning tasks or like settings where there's like chain of thought. So if you're doing math word problems, if you're doing compositional reasoning kinds of tasks, and you're just supervising the model with like really short, simple reasoning problems and asking it to do better on longer, more difficult reasoning problems, that's a setting where the gap grows a bit. That interpretation has a couple caveats that are like in our appendix or something, but I think that interpretation's like basically plausible. That like that's a setting where the gap grows.
Hmm.
If the supervision is just very weak, like very far away from the thing you care about. This is also probably pretty intuitive. Like if you're so we did something where we tested on college STEM questions and we supervised with high school versus 8th grade versus 3rd grade.
Yeah, yeah.
So there's just a bit of a gradient there. Like the high school was as effective as the college, but the 8th grade you're starting to do a little worse, and the 3rd grade you're doing like noticeably worse. Yeah, so we can imagine there's some settings where the gap grows a bit. Overall, we were pretty surprised how effective this like incomplete supervision was. And I think this is mirrored in a lot of I mentioned there's a difference in terminology, easy to hard versus weak to strong, where the OpenAI paper was focused on a slightly different weak to strong setup, still quite analogous.
Yep.
In their appendix, they actually have directly analogous easy to hard results that do the same kind of labeling setup we do. And they also were seeing really positive.
Hmm.
There's like a ratio. Yeah, there's like sorry, it's like a little. You can talk about the effectiveness. You can talk about the ratio. You can talk about the gap. They just also got quite positive results. That like this partial
Right.
supervision ended up being quite good. Seems likely to me that there's something just especially good about getting clean labels versus noisy labels here.
I guess the question is, how is this possible, right? Like this model doesn't know how to do a thing. It doesn't know how to do this really hard thing. You teach it a really easy thing, and then it just like does pretty well on the hard thing. Like we don't
Mm,
like with humans, right? When you've gone through 3rd grade, that isn't sufficient to
mm,
have you graduate from college,
mhm.
right? And yet somehow with language models it is. Like what's going on?
Oh yeah. So I mean, really interesting possibilities here. So one thing I'd point out is I would dispute one of your premises a little bit when you say that, well, language models don't know what's going on. How are they getting all the way there to solving these hard problems? Because I suspect that there are some latent skills or
Hmm.
latent abilities that we're tapping into in the model when we're doing this kind of partial supervision or incomplete supervision. This
Right.
just comes from pre-training. It just seems like it must be the case that in pre-training models will have seen examples of hard problems and potentially either directly learned how to do certain problems, directly memorized certain facts, or just like learn certain facts. I think we're seeing stronger and stronger cases over time that language models are learning like robust generalizable skills that are like interesting skills that are just learned across data points in their pre-training data set. Like you read a bunch of different biology textbooks and you actually start to like learn themes of biology and like some core principles or and in a way that you can think of like individual documents being important for answering a question as just like more like learning some facts about the world. The
Hmm.
true themes of like how to solve math problems or like how to think about chemical reactions being like the skills of doing math or like the skills of doing chemistry. It just seems like models are picking up on these things. And so when we're thinking about what is the effect of easy supervision on a model, it looks something like eliciting task knowledge or like activating task knowledge that you're kind of cueing the model into, okay, I'm doing biology and I need to like do biology in a way that like a college student is supposed to do biology.
It seems like this is kind of related to the discussion on like figuring out beliefs in language models, right? Like if a language model can have this like latent knowledge that like isn't even reflected in its
Mm,
answers to, unless you like fine tune it a little bit on,
mm, mm.
related questions. It seems like that's got to say something about how we're going to understand what it means for a language model to believe something and how we figure it out, right?
Yeah, that's a good point. So I remember when we were talking about simply how one detects beliefs in language models, like how do you even go about saying that the model believes something? I
Hmm.
remember mentioning in the paper we definitely have to make a lot of assumptions about kind of understanding the question, truthfulness, honesty, um, that if you bundle them all together, I think can be kind of analogous to this like task specification thing, where it's like, okay, what am I doing? I'm answering questions truthfully according to
Right.
this person's understanding of the world, or like according to what, uh, hopefully we think of like truth as some kind of objective thing, but like also, also it's always going to be a little bit catered to like our 21st century scientific worldview of like how things work.
Hmm.
Yeah, so so there's something that looks like task specification there, which I think we assumed away in the kind of belief detection case, but really comes to the forefront when we're thinking about easy to hard generalization and how models are even doing this. Yeah. Yeah. So I'll mention there's an extra result which we have in the new camera ready version of the paper, which is now on archive. We compared to something like a trivial prompt, like just giving the model like the simplest possible true statements and like seeing how that does. So
Right.
you just say, okay, what color is the sky normally? Like how many legs does a dog have normally? And then these are questions that, essentially anyone like probably most children could answer, um, as opposed to like third grade questions or eighth grade questions, or I mean, believe me, I could not do any of the college questions in the data. So
Right.
there's something just very basic about trying to strip anything away that's like, is it domain knowledge? Is it math ability? Is it like answering things and like the way an eighth grade science textbook would be written? Trying to strip some of that away and just think about truthfulness. And what was interesting is that these like trivial, truthful prompts did not explain the entire effect of the easy supervision. They explained part of the effect. So it's a little noisy. It's probably somewhere around half. But it seems if you're thinking about how do we get the model to do college biology if we can't do college biology, where, going back to this is like a stand in for how do we get the model to do something really hard that we don't know how to do.
Hmm.
We definitely need to do something that's like convincing it to be truthful and like fine tuning it to be truthful, or mechanistically intervening to get it to be truthful. And then we also need to do something that's like communicating to it that its like task is to like do biology and get it in
Right.
its like
Right.
biology, representation space, task space. Yeah,
Hmm.
yeah. These both seem to contribute to the overall generalization.
So, okay, let's say I take this picture of elicitation kind of for granted, right? The reason we're getting easy to strong generalization, easy to hard generalization, training on the easy things sort of elicits a mode of we're doing this task and we're trying to get it right rather than wrong.
Mm-hmm.
There are kind of two takeaways I could have from this, right? One takeaway is this means that these experiments are just very unrepresentative of the task that we're interested in because we'll want to train CEO bot to do stuff that CEO bot doesn't already know. And the only reason we're getting easy to hard generalization here is that in some sense the language model already knew how to do these
Yeah.
tasks. Another way I could interpret these results is this is actually great news. It turns out that language models know a bunch of stuff that they don't appear to know, and all we have to do is just nudge them on track. So if we want language models to be really good CEOs, all we like it might not seem like they know how to do it, but they actually secretly do, and all you need to do is just like nudge them a little bit to make it happen. Which interpretation is right?
I would describe this more as a difference in use cases, I think.
Okay.
Yeah. So I think we can imagine use cases where there's some extremely capable system that we suspect could do a task very well,
Hmm.
either in the way we want it to or in a way we don't want it to. But we know it's like competent. We know it's capable, and we're just focusing on aligning that thing or eliciting, doing this little bit of steering, eliciting the one task representation rather than the other. But we're basically taking for granted that it's going to be competent and it's going to be able to do the thing well. So that's the kind of use case, and that's the kind of world where it's really strong model.
Yep.
The empirical results we've seen so far feel promising.
Hmm.
Yeah. Get conditioned on that we're doing this thing that's like treating hard test questions that we secretly know the label to as a stand-in for difficult questions that are actually really hard for us to label to. And when we're using big pre-trained language models that like have probably learned a fair amount about this stuff before.
Hmm.
This stuff, yeah, this contrasts with the setting where like we want this model to do something like truly novel.
Hmm.
We have no idea how to do it. We don't know if the agent knows how to do it. We want the agent to try to do it, and to try to do it in like an aligned way, in a way that would be good for people. But we don't even necessarily have a reason to think that like it would already know how based on its training data. And this use case, this kind of hypothetical world, looks a lot more like classical research and compositional generalization in NLP,
Hmm.
where people have for a long time studied settings where like the training data does not have the information you need to actually solve the test problem. And we know that. The
Hmm.
test problem requires a particular kind of architecture, a particular kind of bias in the learning system that would lead the learning system to like learn the right abstractions from the trained data and combine them in the right way that would lead it to get the test problem correctly. And so we one thing we do in the paper is we speculate a little bit about why our results look a lot different from previous compositional generalization research in NLP,
Hmm.
where people have looked at the ability of language models to do, for instance, this kind of like length generalization before. And there have been a lot of previous um, results that in certain language learning settings, um, other kinds of NLP tasks, like when the training data looks different from the test data, and like the test data includes questions that are compositional and those skills are not directly represented in the training data, neural networks often really fail at that kind of
Hmm.
generalization. It's often just really hard for neural networks to generalize to these like kind of entirely novel problems that require combining known things in exactly the right way. And so we speculate in the paper that we were guessing this has a lot to do with pre-training, and it has a lot to do with there already being some of the right building blocks in place, and language models becoming increasingly good at like combining those building blocks based on an incomplete partial amount of supervision. But I'd point to, for more concrete research in this direction, I'd point to some work from Brendan Lake, who's a cognitive scientist at NYU, who they and I yeah certainly some other NLP people who I might be able to remember later, um, are looking really directly at like tests for compositional generalization ability, and particularly some of Brendan Lake's work, I think, has started to tease together a bit. When do you need really strong architectural assumptions? When do you really need really strong biases and models to like learn the right generalization patterns from limited data? Uh, or like when will neural networks actually be able to pull this off, basically, and actually be able to do the entirely novel thing?
This also gets me a bit back to this question of how representative is this of hard problems. And one concern I think a lot of people in the XRIS community have is generalization of alignment versus capabilities, where a thing people imagine is like, look, if you learn a little bit, like it's just really valuable to just keep on knowing stuff. But if you're playing along with a human for some period of time, that doesn't necessarily mean you're going to play along later, right? So I think a thing you said earlier is imagine you have a setting where the AI, has a bunch of knowledge and it like knows how to be aligned or it knows how to be misaligned.
Mm.
And we're going to give it some examples of doing stuff that we want to, fine tune it on somehow. I think a concern a lot of people have is like, well, it's plausible that the generalization it learns is, play nice with humans when you can, or, do whatever is necessary to achieve your secret goal of, taking over the universe and replacing everything with cream cheese. And like for now, that goal involves like playing nicely with people. I'm wondering, and so to the degree that you like really worry about this, um, it's possible that this is going to reduce how much you trust these preliminary, easy to hard generalization results as saying much about the difficult case. So I wonder, yeah, what do you think about these concerns, and yeah, how do you think they play into how we interpret the results in your paper?
Yeah, so this is a good question because I think it's fair to try to contrast some of these like, okay, you can do math, you can do biology kinds of tasks with like learning human values and like learning to act in a way in an environment that like preserves human values. Um, these just feel like different things, and yeah, particularly we would expect, you know, during pre-training and to an extent during RLHF, like these different kinds of information to like be like instrumentally useful to different degrees. Like you're like this is my understanding of your question is like, um, yeah, there's going to be a bunch of settings where like it's useful for the model to know all kinds of stuff about the world, but like whether or not it like needs to have learned our values and like be robustly aligned with our values when it's
Yep.
deployed is like maybe less clear just based on the way pre-training is done or the way RLHF is done. This is a really good
Yeah.
question. Yeah, I think I'm excited about this kind of easy to hard, weak to strong work with reward modeling and in RLHF setting, where this wasn't something we looked at, but OpenAI looked at this, and I believe yeah other people are currently building on this as well. Um, Trying to get a sense of how the problem looks in a reward modeling or like reward inference setting, where like
Right.
we partially specify things that we care about, or like the environment's really big and like it's always hard to say exhaustively when everyone was harmed or not, or like exactly how good or bad an action was for the people involved. uh, so we give incomplete supervision to the model about our values and what states are good for us or not, or like good for users or good, yeah, you know, and and we see how aligned the model actually is tests where we actually take the time to then inspect, like, okay, would this behavior have been harmful? Would this behavior have been uh, aligned?
Mm.
I think the trick in the experiment design here is still that like we need a setting where we can check. So this is like the college route. We actually do have the answers to the hard questions, and so we end up doing the same kind of thing in like the reward modeling or reward learning setup, where well at some point we need to think of like, what would the questions we could ask the model be that we know what counts as a good response or not. What would be the scenarios we would deploy the model in that based on the model behavior it was safe or not,
Mm.
in order to we need those scenarios to figure out what this gap is. So like how effective was the supervision relative to perfect supervision? Was it 60% as effective? Was it 90% as effective? Is it effective enough that we then trust, based on our incomplete ability to supervise the models, that they will be robustly value aligned? I think
Mm.
that part has a lot in common. It could be that the results just simply look worse due to some fundamental differences in what gets learned during pre-training.
I guess I'd like to move on a little bit and just talk about just methodological questions because I think there are a few really interesting ones that come up in this paper, or this line of work. So the first is we've talked a little bit about the distinction between this easy to hard generalization paper and a paper that I believe roughly concurrently came out of OpenAI, weak to strong generalization. And it seems like when I first saw them, I'm like, oh, they accidentally did exactly the same thing. And then you read them a bit carefully, and I'm like, oh no, it's like kind of different. Like, so it seems like to me the biggest difference that I at least noticed is it seems like your work is train on easy problems, and then how good are you at hard problems? Whereas the OpenAI version seems more like uh suppose you get trained, like the problems are just as difficult, but you initially get trained on data where like the person grading how good the answers were just wasn't very good at their job. Do you generalize to like being actually really getting the right answer even though the grader was noisy? I should say it's been a while since I read the weak to strong generalization paper, so
I can actually, if it helps, I can try to rattle off some of the differences that I've noted, as we've been giving talks about the paper.
yeah.
Yeah, because certainly they look pretty similar at a high level.
Yeah, I think I'm most interested in the like in this axis of difference. But I'm not sure I'm characterizing it correctly.
Okay, well, yeah, let's. I'm happy to focus on that one axis, but if you can try to describe it again for me, we could start from there.
Yeah, just this question of like easy to hard generalization where you have the right answers to easy problems and you're trying to generalize to the right answers to hard problems.
Yeah,
My
yeah.
recollection of OpenAI is like their kind of inaccurate to accurate grader generalization.
Yeah, so this does seem like an important difference, and I think you can tell it's an important difference even based on the empirical results we've seen so far. So if you compare some of the weak to strong results versus the easy to hard results in the OpenAI paper, I think they were also seeing that the easy to hard results looked better, were more promising, kind of similar to ours. So it seemed like the models were generalizing better from cleanly labeled easy data as opposed to noisily labeled like all of the data.
Yep.
I think you can tie these two labeling approaches together in the same universal framework. I think you can.
Hmm.
So what you suppose is that you have a labeler and they write down soft labels for data points, but they could write down hard labels for data points. So they might be perfectly confident in what the label is, and so they basically put like probability 1 for something or 0.99. They might be uncertain, so they like write down probabilities for what the label should be. Um, and they're calibrated to some extent. Maybe they're perfectly calibrated. We might just assume they're perfectly calibrated.
Hmm.
And so what easy to hard looks like is supposing like the the labeler can get all of the easy problems correct, and they know that they can get them correct,
Yep.
and they can't get the hard problems correct, and they know that they can't get the hard problems correct, and then you sort the data based on the label probabilities.
Yep.
When the labeler is confident that they don't know the answer to a hard question, they are uncertain over all the labels to the hard question. And when they're confident that they know the answer to an easy question, they are certain that one label is correct. So that distribution looks like 1000 versus like 0.25, 0.25, 0.25, 0.25. And you sort the data
Hmm.
based on like the entropy of these distributions, based on how peaky they are, and that's how you get easy to hard. So this is a kind of labeler that you have in mind. They can do easy stuff, they can't do hard stuff, and they know what they can and can't do.
Right.
This labeler, there's like a smooth transition from this labeler to the weak labeler. The weak
Hmm.
labeler just does their best on all of the data, and they know most of the easy problems and some of the medium problems and very few of the hard problems. And you might say that they might still be perfectly calibrated, but so two things change. One, the labeler changes a little bit. Like we're supposing they don't get all the easy problems, they just get most of them. They get a medium number of the medium problems correctly, and they get some of the hard problems correctly. They don't get none of the hard problems correctly. Maybe there's some super hard problems where they don't get any of them. So the labeler changes a little bit. The labeler doesn't have to change, but what really changes is the kind of sorting mechanism for getting the training data set, where we're not using a hard cutoff anymore. We're actually going to include hard data that is just noisily labeled. And I think this is how some of the methods work in the OpenAI succeeds, is that they're leveraging some kind of like noisy label learning approaches to be able to say like, okay, well, it's just what happens if you know that the data is noisily labeled. How could you still learn something from that?
Right. Right.
So there's just this kind of continuous spectrum in terms of like which parts of the data distribution the labeler knows, how calibrated they are, and then how you decide to translate those uncertain labels into a training data set. It
Yeah.
looks like domain shift, you're thinking about easy to hard domain shift. It looks like noisy labels, you're thinking about noisy labels learning.
Broadly, a thing I'm a fan of is just like now that these papers are out, this is like an easier distinction to notice.
Mm.
Like 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 I might have not noticed these were like different ways in which you can have like easy to difficult generalization, and now we can just like think about, okay, which of these regimes are we in? We
Mm.
notice that they're
Mm.
kind of different. Like, I think this is cool. And related to this, I actually want to talk about notions of hardness in your paper. So, like, in order to do this easy to hard generalization, you have to like rank problems by how hard they are, and train on the easier ones, and then do something on the harder ones, right?
Yeah.
And you have a really cool thing about your paper, in my opinion, is you have like multiple different notions of hardness, and you talk a little bit about they're mostly correlated, but they're not actually entirely correlated.
Yeah.
And I think I really want to know is like, what do we know about the different types of hardness, and like which ones should I pay attention to?
Yeah, absolutely. So, and this is another big difference with the OpenAI work, where, um, and this is not a weakness of their work. It's just they choose a more abstract approach, which is they're thinking, let's. It's like they say we have some arbitrary labeler and they have some kind of arbitrary capability, so let's just use a model as a stand-in for that, and they
Right.
have a model label the data. And we take a different approach. We take a very empirical approach and just say, okay, what metadata do we have? What metadata can we get for like hardness?
Sure.
And so we're looking at grade level for ARC, which is a science QA data set. We have a couple other annotations that are really interesting.
Hmm.
So like there's like a psychological skills scale it's called the
Hmm.
Bloom skills. It goes from 1 to 5, where 1 is like the simplest kind of like factual association, almost like rote memorization, and 5 is like the most complex thing you could imagine, like analyzing a complicated argument and like formulating a counter argument and then using that to decide what the answer to a question is. And so it's
Right.
like a hierarchy of reasoning skills that psychologists use as they're thinking about construct, and like psychologists and educators use as they're thinking about constructing test questions, where like
Hmm.
just a rote memorization test question is easier than like a synthesized counter argument test question. And then there was one one last annotation we had for the ARC data. So besides grade level and Bloom skill, we just had like a 1, 2, 3 difficulty level. So I just
Okay.
and we actually I don't know where that comes from. I think some of the data set collectors know where that comes from. But this was interesting because this is something that the educators designed as intentionally orthogonal to grade level. So you can
Huh.
imagine that when you're designing a test for 8th graders, you don't want all the test questions to be the same difficulty, because one thing you're doing is you're ranking students. So
Yep.
you want some of the questions to be easier and some of the questions to be harder. So grade level on its own, if you're just pulling questions from exams, the way people write exams, grade level on its own is not a perfect indicator of difficulty, because we
Right.
use exams for rank ordering students. So there's
Yeah.
naturally overlap in the difficulty between and across grade levels by design, and you see this exactly in the data where this expert 1, 2, 3 difficulty gets designed as a within grade level difficulty thing. So it just ends up being orthogonal to the grade level difficulty itself.
Yeah. Should I think of this as kind of like grade level difficulty is something about like difficulty of like just understanding the domain at all, whereas 1, 2, 3 difficulty is like, okay, you know the basic facts, like how hard is it to reason about this thing?
This is the end of my um, ability to like confidently
Fair
comment
enough.
on these things. Yeah, but that was those were ones for ARC. We had grade level for MMLU. Um, the main thing we used with GSM8K and strategy QA is this like number of reasoning steps. So this is
Yep.
the measure of compositional difficulty. How many subproblems did you have to solve on the way to solving the overall problem?
Hmm.
And subproblems are nice to think about because it's just like kind of like axiomatically a measure of difficulty. Like if there are problems that require, like if there's a problem that requires 7 steps versus a problem that requires 6 steps, and each step is itself of the same difficulty, you just know that the problem that requires 7 steps is harder because it's just like one
Right.
more chance to be wrong. That was one we looked at for those problems. And then there's kind of like basic stuff like question length, answer length was something we looked at. We also had a model based difficulty measurement. We didn't just use model zero shot label probability for sorting data. We actually used a minimum description length based measure, but it's roughly similar idea.
Yeah.
So we had a model based measurement too. Yeah, and then yeah, you look at how all these things correlate, and they don't correlate that strongly.
Yeah.
Which, so there's a lot of ways to read that. I mean, you can read that as data noise. I think I favor reading it as like problems vary along many dimensions, and among some dimensions they might be harder, and along other dimensions they might be easier. Maybe you have a hard reasoning problem about like very general knowledge, or maybe you have a very easy reasoning problem about very specific domain knowledge. That'd
Right.
be just two axes to think about. But because problems vary along all these dimensions, it's just kind of rare that like this is not really the way we design tests. Basically, for the reason I just mentioned, we don't design tests and like we don't collect data sets or like we don't collect questions about things in the world in the way that like all of the most niche domain scientific questions we can ask also require a ton of reasoning and also require like really complicated higher order reasoning. And then all of the
Right.
very basic factual association questions don't require any reasoning and like are just a matter of association. And like it's not the you just wouldn't expect all of these latent factors to be perfectly correlated because that's not the way we ask questions about the world.
Sure. And I guess because these aren't correlated, it strikes me as possible that you might, after having done this paper, be able to say something like, oh, easy to strong generalization works really well when the notion of hardness is, this minimum description length principle. Which, by the way, so I wasn't familiar with this minimum description length like difficulty thing before I
Mm-hmm.
read your paper. We have little enough time that I don't want to go into it right now, but people should look up the paper Rissanen Data Analysis by Perez et al. 2021. It's like really cool paper.
Yeah, I'd asked Ethan for how to implement this thing because Lena Vojta introduces some work like basically theoretically pitches this MDL metric for
Hmm.
measuring information content, and I read that paper and like loosely understood it, but had no idea what to code up, and Ethan helped me
Right,
code
right.
this up, so
Nice.
that was helpful.
I guess it strikes me as possible that you might be able to say something like, "Oh yeah, easy to strong generalization. It works well when the notion of hardness is like this MDL notion, but it works poorly when it's like number of star or like difficulty out of three
Yeah,
or something like that." Is there something like this that you're able to say, or are they all about as good as each other?
I was hopeful to get to that point, but I don't think we got to that point. And I'm not sure we ultimately have the data to get there because we
Hmm.
kind of just got all the data we could, and it leads to this kind of patchwork of we don't actually have all the variables for every data set.
Right.
So sometimes when one of the variable changes, it's like the domain changes, the data set changes, other difficulty measures change all at the same time. I toyed around with once we had all the data written to file, I toyed around with some regression models where we did try to tease apart what were the important factors, but I'm not really going to make any confident conclusions there. But I would think this would be great follow up work where you fix the domain and start varying all these individual factors, and then see how the results break down by that.
Yeah, I think it's just almost similar to the interpretability, like into what we've learned from interpretability. Like it seems like there's just like different potential notions of what we might mean, and like digging into which one is important seems like pretty pretty high value and like maybe kind of underrated here.
Yeah, yeah. I mean, it would be great if we could pin it down because then if we could
Yeah.
say it's a matter of like how infrequent and rare this factual knowledge is when you're like reading about the world or like how just like specific this kind of thing is. That paints a very different picture compared to like how difficult it is it to like compute the answer to this question? How long does it take to arrive at the answer to this question? Those give very different pictures.
So before we move on, you mentioned like there are a bunch of differences between this paper and Wheat is Strong. Is there one kind of methodological difference that you're like really interested in talking about before I like leave this behind?
We've definitely hit a bunch of them. We talked about the baselines. We talked about how to construct the data set based on kind of like labeler confidence. We talked about the human hardness variables.
Hmm.
Maybe one more. And we talked about even the differences in the results, how positive easy to hard looks versus weak to strong looks.
Yep.
One minor thing I would add that I suppose this is a little bit more in the criticism category. I
Okay.
think a few people were definitely concerned about the early stopping that seem to be important to actually doing the fine tuning in the weak to strong setup.
Okay.
So they're mostly looking at fine tuning models. I think they did some prompting. I don't actually remember if they did prompting or ICL. I think they do. I don't think they do linear probing. So we also tried linear probing in addition to the other fine tuning and prompting.
Hmm.
But there's a when they're doing their fine tuning, there's a little bit of hyperparameter tuning and a little bit of like dev set model selection, like early stopping.
Hmm.
That seemed important. That's so this is important theoretically. So because the idea is like based on incomplete supervision, the right function would still be identifiable. You
Mm.
don't want the right function to be like one of many possible functions, and it just depends on like getting exactly the right amount of fitting to the data, such that
Yeah,
if you're
yeah.
underfit, you're in a bad region, and if you're overfit, you're in a bad region. But if you fit exactly the right amount, you happen to uncover the right function. So one thing that empirically I can point out, we don't do we don't do much of this analysis actually in the paper, but in retrospect, it feels important, is that we could fine tune as much as we wanted. Like, and the longer the ICL prompt, usually the better. Uh, and the more data that went into the linear probe, the better. I mean, the linear probe fits easily, but we could basically fit as much as we wanted to this clean, easy data, and performance would just go up on the hard data, which is great. So, I mean, this problem is clearly not correctly specified. Is it misspecified? I don't know. We couldn't overfit to this
Mm.
signal. So this was something that was interesting to us in retrospect.
Wrapping up a bit, we've talked a bit about like stuff you've worked on. You've actually worked on a bunch more stuff that I didn't have time to go into. If people are interested in following your research, seeing what you've done, how should they go about doing that?
Yeah, well, you can find me on Twitter, and I think we announce basically all of our papers on Twitter, so that's a good way to stay up to date. The handle is Peter B as in boy Hase, but I think you'll find me easily there. Um, and if you're really curious about reading all the PDFs, probably a Google Scholar alerts is something I tend to enjoy for others as well.
All right, great. Well, thanks for coming on Excerpt.
Thanks so much, Daniel. What a pleasure. This was great.
This episode is edited by Jack Garrett, and Amber Dawn Ace helped with the transcription. The opening and closing themes are also by Jack Garrett. Filming occurred at Far Labs. Financial support for this episode was provided by the Long Term Future Fund, along with patrons such as Alexei Malafeyev. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about the podcast, you can email me at feedback@axrp.net.